As previously mentioned, exponential and logarithmic models are extremely useful in various population and radioactive decay modeling situations. This is the simplest growth and decay model. It says that the amount of material or population size present at time t is exponential with some constant in the middle and some initial amount p naught. So let's just label this equation to keep track of it. On the left-hand side, we have the amount or number of things at time t, whereas on the right-hand side, this k stands for the growth or decay constant, depending on the scenario that you are describing. If it is a growth constant, it will be positive. If it's a decay constant, it will be negative. T is, of course, time, and then this P naught is the initial amount. So let's actually sketch the two different scenarios, the positive or the growth scenario and the negative or the decay scenario. So in terms of the graphs, both are exponential functions, and if we're thinking that whether the growth or decay occurs with time, we will be only looking at the positive values of t. So if the constant is positive, that represents exponential growth, I'm going to have some kind of initial amount of, let's say, population or the number of infected individuals. And then afterwards, my function will grow, whereas this is P naught. If K is negative, that represents the decay scenario. I will start with P naught, but my function will exponentially decay. So here I'm not showing you the tail on this end, it's right there. On the decay constant, the negative will be coming from the side of the increase, and then it will be decreasing afterwards. Also notice that this initial amount, we just take the convenience of labeling it P naught, but if I were to actually plug in time equals 0 into the entire equation, I would get P naught e to power k times 0, because now t is 0. And then, of course, this is e to power 0, which is just 1, which results in P naught. That is why that constant in front of the exponential portion here is the initial amount. Australian cane toads, or giant toads, were introduced in Australia in 1935 with the purpose to fight cane beetle, which at the time was the main pest of the sugarcane, which was a big industry in Australia. The native land of these guys is South America. However, their introduction, while seemingly theoretically reasonable, really backfired. What happened was there was a certain asynchrony in the reproductive cycles or life cycles in general of the cane toads and the cane beetles, which meant that while the cane beetles were eating all the sugar cane, the toads were more or less hibernating. The other issue was the fact that the toads reproduce greatly and they have really, really voracious appetite, which is why they were supposed to be really good for eating cane beetles. Unfortunately, the other huge issue is the fact that their skin is extremely poisonous, which makes them almost invincible to all types of predators. And in fact, they've been labeled one of the worst pests because they have no natural predator and they're also poisonous to domesticated animals as well. Since then, the government has tried a number of techniques to control the population and more or less not really successfully, which serves as another lesson that if you mess with an ecosystem, you might have another thing coming. Now, because this is such a big issue, their population and particularly the spread of the territory they're covering have been greatly studied. They've been studied since 1939. They were introduced in 1935. And we will first use this simplified model to track or try to model what their territorial coverage has been throughout the years. Year 0 will correspond to the first year we have data for, which is 1939. So the first question is, if I have two pieces of information. In 1939, they occupied 35,800 square kilometers, and in 1949, they occupied 73,600 kilometers. I would like to find what we call a solution to this model, which really means finding the unknowns, which in this case are the initial population and the growth/decay constant. Okay, so let's write out all the pieces of information that we actually have here, which of course is, first of all, in the year 1939, we have that the total occupied area was 32,800, which means that at time t equals 0, once again, I can either remember that this stands for the initial amount, or I can plug in t equals 0, and we will see that A naught is equal to 32,800. The next piece of information that I have something about is the year 1949, which then of course corresponds to t equals 10. And then I know that the total occupied area was 73,600. So this number corresponds to the right-hand side of this equation. I already know the number for A naught, R is what I'm after, and T will be 10. Okay, so overall, I have the equation that 73,600 equals to A naught, which is 32,800 e to power R, which I still don't know, times T, which is 10. This is really good news because this is an equation with only one unknown, R, and I can solve it for R. So solving for R here, I will have that it is the logarithm of 73,600 divided by 32,800 all over 10, and that comes out to be approximately 0.081. Okay, which means that now I know all of the constants in my model, and I can rewrite this as A naught is 32,800 e to power R, which is 0.081 t. I can see that this is indeed a growth model because the value for R is positive. And with that in mind, I can approach the second part of the question that says, now using my newly discovered model, I am going to estimate the area occupied by toads in 2020 with the, of course, assumption that the model back from the 30s and 40s still works. So with no great changes to the environment. So what happens in 2020 is the total amount is going to be 32,800 e to power 0.081 times t that corresponds to 2020. Well, t equals 0 corresponding to 1939. So t that corresponds to 2020 will be 2020 minus 1939. Okay, so plugging all of this back in, I'm going to get approximately 22,856,304 kilometers square. So of course, unbounded growth ends up in really, really fast spread if nothing actually happens in terms of the control of the pest.
In this next example here, we will use the basic population model to actually compare two populations. In this case, there are two populations of fish in Cultus Lake. Sturgeon population is described by this population model, and rainbow trout population obeys the following equation. So we have a few questions that are concerning these two populations. Which of them is growing and which is declining, if any? So let me rewrite the equation for the sturgeon. Here we have S naught that corresponds to the initial population, and we notice, of course, that the exponential here has a negative constant in its degree, which means that the population of sturgeon is declining. On the other hand, if we take a look at the rainbow trout population equation, we have R naught that corresponds to the initial population there to the power of 1.7 t. The constant here is positive, which means that this population is in fact growing. The next equation is giving us the initial levels for both populations, 300 for the sturgeon and 1300 for the rainbow trout, asking what time would the two populations be exactly equal? So first of all, what we're going to do is, in fact, match the initial levels to our constants in the equations. So 300 for S naught and 1300 for R naught here. If we would like the two populations to be exactly equal, we will then set the two equations to be equal to each other and solve for the corresponding t. So what we're going to have is 300 e to power minus 1.3t, which corresponds to the sturgeon population, equals to 1300 e to power 1.7t, which then corresponds to the rainbow trout population. And we're solving for them to be equal to each other. Now, I encourage you to here pause the video and actually try to solve this equation for yourself. There's a number of different ways you can do so, and then come back and see which one I choose. Okay, so let's say we're back and you've actually tried out this equation. As I said, there's a number of different ways to do so. Because everything in the equation is positive, the exponentials never are equal to 0, I can safely divide things. So let's say I'm going to move all the constants to the left-hand side. So I'm going to divide everything by 1300. And I'm going to move all the t's to the right-hand side. So I'm going to divide both sides by e to the power of negative 1.3t. So what I'm going to have is on the left, 300 over 13,000, and on the right, I'm going to have what I already had there, e to power 1.7t, divided by e to the power minus 1.3t. Recall that if the bases are equal, then exponential rules suggest that we simply subtract the powers. So it's going to be 1.7t minus negative 1.3t. So let's combine what we have on the right-hand side. On the left, I'm going to keep my constant, and on the right, I'm going to have minus minus, of course, turns into a plus. So I have e to power 3t. Now I can take logarithms of both left and right-hand side and divide by 3 in the exponent here. So in terms of t, I am going to end up with, once I plug it into the calculator to calculate the logarithm of this quotient, is minus 1.46 divided by 3. Now this is a little concerning because remember that t was measured in years. So what I have just gotten as the answer is negative number of years, which of course is not biologically possible. So in terms of math, this is the solution to the corresponding equation. In terms of the biological content, there is no solutions for the positive values of time. Now, that means that biologically, these two populations are never equal to each other. Let's, in fact, do the point 3 here and sketch both of the graphs in order to better visualize what might have happened and why we have gotten no solutions. Now, again, in general, biologically here, I'm only interested in the values for t being greater than 0, but I'm going to include some negative values just so I can see for completeness the mathematical models drawn for negative values of t as well. So what do I have for sturgeon here? I have that the initial population is 300. So let me sketch 300 here, let's say up here, and the population is declining because the exponent is negative, which means that I have a exponential model that is that of the decay. Okay, so I'm sketching this in dashed lines because, again, this is not something I would consider in the context of the actual population, but it is a mathematical model that it describes it. For the rainbow trout, my initial number is 1300, so I'm going to sketch that. Now note that my sketch is going to be not at all to scale, but just qualitatively showing what is happening. And the rainbow trout is in fact growing because the exponent here is positive, which means that I have an exponential function here that is in fact increasing. So here we can clearly see on the graph that for positive values of t, these two curves will not intersect, producing no solutions there, but they will in fact intersect on the negative side, which corresponds to the mathematical solution here. Let's think about that in terms of the actual content again. So I have a sturgeon population that starts at a lower number and is decreasing, and I have a rainbow trout population that starts at a greater number and is increasing. Well, of course, the two of them will never be equal as populations. So producing no solutions is also okay, and this in fact does happen. Let's take a look at the two other ways that we can describe population growth and radioactive decay. And these are the concepts of half-life and doubling time, each corresponding to whether the function is that of growth or of decay. On this slide, we're going to see how those two concepts are actually similar. So for population growth, we have a differential equation that states that the rate of growth is proportional to the size of the population. If we're talking about the growth, then this constant of proportionality is going to be positive. And if the population is growing, then we can of course discuss things like doubling time, meaning when is the population going to be twice the size that it started with. So as a first step, we're going to transform the differential equation into the equation for population growth or into its solution. So what I have here is that the population size is equal to the initial population times e to the power of the constant of growth times the time. Okay, now again, if I'm interested in the doubling time, that means that if I started with P naught, I would like to know at which point the population size is going to be twice the initial. So the population size I'm after is twice P naught, and I want to know when does that equal to the population at this time. So I'm trying to solve for t here, k being some sort of constant. First of all, I'm not starting with the zero population, so I can divide both sides by p naught and cancel those out. And then the next equation I'm going to have is 2 equals e to power kt. I can take logarithms of both sides and then use the logarithmic rules on the right-hand side to simplify the expression here. And so what I have is ln 2 is equal to kt, and again, k being a constant, I am solving for t here, which comes out to be ln 2 divided by k. So this, if you know the constant of growth, this is the time at which the initial population will double. On the flip side, let's discuss the radioactive decay. So the differential equation for it here is stating that the rate at which the radioactive material decays is negatively proportional to the amount of material left. Now, in order to explicitly state that it's negatively proportional, I am going to insist on including this minus here, and then to ensure that this quantity is in fact negative, I actually have to state that k itself is positive. Because if this was negative inside, the negative of a negative would have produced a positive number. By explicitly including the minus, I have to ensure that the constant itself stays positive. Now, we're going to follow a very similar process, but for a new equation here. So first things first, I'm going to turn this differential equation into the actual solution. So what I have is the amount of radioactive material is the initial amount times e to the power of the constant of decay, which is minus k times the time. And because it's decaying, I'm interested in half-life. So the amount of time that passes before I have exactly half the amount of material left. If I start with R naught, that means I'm interested in the value for t at which there's exactly half of R naught left. So my equation here is going to be half of R naught is equal to R naught e to the negative kt. Again, I can actually divide both sides by R naught, assuming that it's not negative, and my next equation is going to be 1/2 is equal to e to the power of negative kt. I can take logarithm of both sides, and what I will have is ln of 1/2 is equal to minus kt. Now, I can solve for t here, but I can also simplify this expression a little bit by realizing that ln of 1/2 is the same as negative ln of 2. And then my equation will turn into negative ln 2 is equal to negative kt. Pause the video for a second just to persuade yourself that these two quantities are actually the same. You can pull out a calculator and calculate this first and note that that is in fact the case, or you can really go through the simplifications following the logarithmic rules to practice them a little bit more. Now, looking at this equation here, I notice that there's minus on both sides, so I can cancel that out. turning this into ln of 2 equals to kt, and then solving for t, I have ln of 2 divided by k. Now note that the surprising thing is that both of these are actually exactly the same. So if I insist on keeping the constant positive and including a separate minus, then the concept of half-life in the radioactive decay is very analogous to the concept of doubling time in the population growth example, to the point where the way to calculate them is going to lead to the exact same formula. Now, once we have derived the formula, we can actually use the formula directly. So if you have a question that's asking for a doubling time or a half-life, you can of course go through the setup process and find the time this way, or if you have the formula on hand, you can simply call upon the formula to help you solve the question a little bit more efficiently. Let's take a look at an application of how to use these formulas in the specific setup. So the specific setup I'm going to use is that of the Chernobyl disaster, on which we have lots of data by now. And it's actually personally important to me because everybody is aware that Chernobyl happened in Ukraine. Very few people are aware that Chernobyl actually happened on the border between Ukraine and Belarus. And I happen to be exactly from Belarus, from Minsk, just about here. So let's take a look at some of the data that we have from there. The Chernobyl disaster happened in 1986. And it released in particular large quantities of iodine-131 and cesium-137. These two elements are well studied in a lab, and therefore we actually know their half-lives. Iodine-131 has a half-life of 8 days, so very short half-life, whereas cesium-137 has a half-life of 30 years, which will bring us to about this time right now. What we're wondering is how much of these materials actually remain present today. I'm going to solve this problem for iodine-131, and I encourage you to actually do this for cesium-137. So what do I have in terms of the equation for iodine-131? I know that it decays exponentially, so I'm going to assume that it decays simply exponentially, which means that it follows the exact equation I had on the previous slide that says that the rate of the decay is negatively proportional to the amount of material present. What I don't know yet is I am given what the half-life is, but I don't actually know what this constant K is equal to. So this will be my first order of business, finding K. I can set up the equation from scratch again, but what I'm going to do is actually use what we have derived on the last slide. So from the last slide, what we found out is if I set up the equation this way, explicitly including the minus here, is that, let's take a look, that T, the half-life, is equal to ln of 2 equals to K. Now, I can actually solve this equation the other way around for K instead of T. In this case, I know the half-life and I need to know the K, so this equation will be useful if it's solved for K instead of T. And I can note that this will give me that K is equal to ln 2 divided by T. Now, we have to decide what are the units of time that we're going to use. The half-life of iodine is given in days, but our timeline is sort of given in years, and I would like to know how much there is present today, which is more than 30 years from then. So I have to decide whether it is days I'm going to use or years. I'm going to use years, which means that first of all, I have to convert 8 days into years. I'm going to skip the calculations for that and include simply a number. 8 days in years is 0.021917. So let me note here that this is 8 days in years. Now, if I simply calculate this number as a K, it turns out to be approximately 31.626. So that gives me that I can plug this as the value of K into my model. So overall, I have that dr by dt is equal to negative 31.626 of R. Okay, again, just quick common sense check that this is negative, meaning that this is in fact a decay, and we are in good shape. This is the differential equation. I would like to know exactly how much material still remains today, so I am after the solution here. Again, recalling that the solution will give me the amount present today is equal to the initial amount, e to the power of the constant, so minus 31.626 t, which means that I can now calculate the current amount by simply plugging in the value for t at which I'm interested. Now again, because I've decided that I'm going to use years as units, I simply have to calculate years of that have passed since 1986, and that is in 2021 going to be 35 years. I'm going to plug 35 in for t here. Let me write this out. So I'm going to have R naught e to power minus 31.626 times 35 years. And then you can plug this into a calculator to figure out what constant this actually gives you, or what number it actually gives you. And you're going to notice that this gives you 0. Well, is this something that we actually expect to have happened? That there is almost no, or in limit, no amount of iodine 131 left? Yes, I think that makes perfect sense. If the half-life is 8 days, that means that every 8 days, half of the material goes away, and it has been 35 years worth of time that passed between then and now, which means that by now, there's none of the iodine 131 left. You can also, I'm not going to go through the calculations, I'm going to leave the calculations for cesium-137 to you, but you can also establish an expectation of what you expect your answer to be there. The half-life of cesium is 30 years, and it's been 35 years since then. So what you expect is to see the initial number times approximately a half, because by now, approximately a half, just over a half of cesium-137 would have actually decayed in the ecosystem. In this next example, we're going to consider general setup for organismal growth. We will have to make some simplifying assumptions along the way, but this is going to be generally a reasonable approach to think about how cells grow. We're going to start with a cubic cell, just so that we can have a handle on the shape of the cell, with side length L and mass M. So altogether, what we're thinking about, just so we have all the same picture in our heads, is a cube of side length L. Now, I am interested in the mass of the cell, and in fact, what I would really like to know is how does the mass change as the side length changes and the entire cell grows? So first, I would like some kind of relationship between the mass and the size of the cell. Now, one such relationship is given by density times volume being equal to the mass. Okay, if the cell is little, then I can assume that density is uniform throughout and therefore constant. So let's assign some kind of constant to the density. Let's call it D. And in terms of volume, if I have a cube of side length L, then I know that the volume is going to be L times L times L, or L cubed. So altogether, from this equation, I have that my mass is equal to some density constant times L cubed for the volume of the cell. If I'm interested in how these things are related to each other as the cell grows, I am interested in the derivative of this expression taken with respect to time. So I'm going to recall how we actually take derivatives with respect to time of all the things that change with respect to time. And from Calculus 1, you can remember concepts, or rather techniques, such as related rates problems. I'm going to take a derivative of this entire equation as stated. Keep it in mind that everything is dependent on time. So mass, as it changes with respect to time, will produce a derivative of dm by dt. On the right-hand side, if I take a derivative with respect to time, the density is a constant, so it will stay put, and then I have to take a derivative of L cubed. According to the chain rule, I first take the derivative of the outside function, which is the cube here, so 3L squared, and then I have to follow up by the derivative of the inside, which is L itself, which itself will change with time, so this will be followed up by the derivative of dl by dt. I don't know it explicitly, but I don't have to. I will simply think of it as an expression of the rate of change of the side length with respect to time. Now, what I'm actually going to do is derive the expression for dm by dt, the change in mass with time, in a different way. So let's take a look at some biological processes that occur within the cell. The cell ingests food at the rate proportional to its surface area, and that is because it ingests food by allowing it to permeate through the membranes from the outside. Now, that means that I have some sort of proportionality constant times the surface area. The surface area of the cube are going to be all of the faces of the cube, each one of which has area of L squared. Now, there are 6 of them, but I also have the proportionality constant for the ingestion, so I'm going to call this proportionality constant S, and so the whole thing is going to be proportional to SL squared. Again, I know that there's 6 faces of the cube, but I already have the proportionality constant here, so this 6 got basically absorbed into the proportionality constant S. On the other hand, the cell consumes food at the rate proportional to its volume. It has to actually sustain life throughout the entire cell, so it's proportional to the volume. I'm going to call the proportionality constant here V, and the volume, as discussed before, is actually L cubed. Now, that means that the cell's mass changes with absorption of nutrients and consumption of nutrients. Absorption, of course, affects the actual mass positively. It adds to the mass, whereas the consumption is something that we have to subtract because this is what cell needs to consume to live, and therefore the nutrients actually go away and do not make cell larger. Now, luckily for us, absorption and consumption are exactly the things that we have just derived, so we can plug them in. Absorption is going to be SL squared, and consumption is going to be VL cubed. Now, what we're going to remember is that we actually already derived an expression for dm by dt. Here it is. So these have to describe the same exact phenomenon. Therefore, the 2 expressions for it can be set to be equal, and then we can see what else inside of this we can solve for. So what I'm going to do is simply take this expression and rewrite this in the equation together with the new way to describe the dm by dt that I have just come up with. So all I have here then is an equation that connects quite a few of the variables. Now recall that S, V, and D are simply constants of proportionality, whether density or volume or surface area proportionality. And so in terms of my unknowns, I have the length of the side of the cube and how fast that grows. We're going to use this to solve for dl by dt. So let's make a note here. I'd like to solve for dl by dt. I encourage you to pause the video for a second and actually try to solve this equation for dl by dt, keeping in mind that you're essentially going to treat everything else as constant for now. You're going to isolate dl by dt and then simplify the expression as much as you can. Pause the video, see if you can do it. The expression we should get for dl by dt in this case is going to be SL squared minus VL cubed, the entire right-hand side here, divided by the coefficient in front of my dl by dt. So divided by d times 3L squared. What I'm going to do next is actually simplify this expression a little bit. I know that this is a lot of constant and sometimes can be kind of difficult to stare at, but bear with me here, we're almost there. So what I'm going to do is basically undo the common denominators with this minus. I have this fraction here minus this other fraction here. So let's take it a little bit slowly. I have SL squared over d times 3L squared minus VL cubed divided by d times 3L squared. And now I can notice that I can actually simplify things quite a bit, right? For example, L squares here will cancel out. L will cancel out, a number of L's will cancel out here. So what I have altogether in a simplified version is S divided by 3D minus V divided by 3D times L, right? So all of the L's got canceled here, but I still have one L remaining here. This is a constant because this is just the surface proportionality constant and the density, and this is also a constant for the exact same reasons. So let's give these guys names. Let's say we'll call this K1 and we'll call this K2. So I can rewrite this expression in a slightly more pleasing way without too many constants. K1 minus K2L. So what we have here is the equation dl by dt is equal to K1 minus K2L. So this is saying that the rate of growth of the side length is negatively proportional to the side length itself with some other constant added to it. Note that this equation is not the same as the basic time that we've been solving so far, where I have, for example, dp by dt is equal to kp. There is more to it on the right-hand side here. So this is a new equation for us, and we're going to have to come up with a new solution to something like this. And this is another topic that we're going to consider for the next class. For the last thing in this lecture, let's simply think about how we can set up differential equations for different scenarios and where we will see the different types of equations. So here we have the population grows at an annual rate of 1.25%. So this is saying that the population growth is proportional to the current population size with a proportionality rate of 1.25%. So the differential equation will be the proportionality or the rate of growth of the population is proportional with the proportionality constant of 1.25%. Remember, percent means divided by 100 times the size of the population itself. The next one, radioactive sample loses 5.6% of its mass every day. So in terms of the differential equation, that means that I have a negative proportionality constant of minus 0.056. And the corresponding differential equation then is going to be minus 0.056 of R, right? Again, recall that this is saying that the rate at which the material decays is negatively proportional with this constant to the amount of material still present. The next example is a bit more complicated because there's two pieces of information we have to keep in mind. Your bank account earns 4% of interest every year, which is very similar to our first problem here. It's 4% of whatever you have in the account. So I can start setting up my equation. Let's say the amount of money is going to be A. So the rate at which it grows is proportional with 4% proportionality to the amount of money I have in the account already. However, I still have a second sentence to go here. At the same time, you withdraw money from the account at the rate of $1,000 per year. Notice that this 1,000 is not proportional to whatever you have in the amount in the bank account already, right? So whether you have 2,000 there or 2 million there, you're going to withdraw $1,000. 4% relates particularly to the amount you already have in the account. $1,000 is simply a constant withdrawal. So the rate of change of the money in your account depends 4% on what you earn with interest minus $1,000 that is a constant by itself, does not get multiplied by A because it is completely independent of whatever else you have in the account. And here, you notice the exact same type of equation that we have just seen with the organismal growth. You have a part that is proportional to the amount that's present, and you have a constant part that does not depend on that. And again, whereas the first two equations are something we have solutions for, this last one is something we're going to have to examine a little bit closer. Let's take a little last example here, which is particularly relevant to our pandemic situation we're all in right now. This is a well-known principle of how epidemics actually spread. The rate at which an epidemic spreads is proportional to the product of the number of people who have caught the disease and the number of people who have not. So this is a key word here. It's proportional to the product. Let's think about what does that first of all mean for the epidemic to spread. Epidemic spreads, meaning that the number of infected individuals changes or increases. So we're going to have to think of the individuals that are infected or the ones that have already caught the disease. Let's call this group infected and label them with a variable I. And we also have the people who have not yet caught the disease. These we're going to call susceptible because they're susceptible to the disease. This is the vaccine-free scenario for now, and we're going to call them S. So now what we have is that the way the epidemic spreads, the rate at which it spreads, so the rate at which the infected individuals, the number of infected individuals grow, is proportional, so I have the constant of proportionality, to the product of the number of infected individuals and the number of susceptible ones. So proportional to I times S. And this is yet another differential equation we have not yet seen before. The number of infected individuals isn't just growing as a proportion of itself, but rather as a product with something else. So these two types of equations are something we're going to be studying throughout the rest of the course and something we're going to have to find solutions for as well.